Here we are, finally. So, hello back. So, as I was saying, we recently put on the archive a long review on quantum Fisher information. And let me present you the rest of the people. Here, Paola Buso in the first row. Then there's Dario De Santis, who's now in Pisa and Normale. And Jacopo Surace, who's in Perimeter, he's in ICFO now. He will go to Perimeter Institute in September. So since it's a long review, I'll just give you some shameless self-promotion at the beginning. And if you open the archive, the first page looks like this. And then you scroll to the second page, and you find this long index. And basically, everything you want to know about this 60 pages long review is written here. It's like you don't need anything else. You just go there, and it's like it's full of hyperlinks, and there's everything. It's like really a summary of everything you need. Then another thing we use in this paper to make it a bit more readable is these green boxes that tell you which is important, like the main part of the text, and some additional information in the review. And now that we did the useless self-promotion part, let's go to the physics. So Fisher information is a statistical distance. So it is useful to give you an idea of what statistical distances might be. And I do this with a game. That is, consider you have this sentence in a language that you don't know, and you want to guess which language it is. So one way of doing it is you take an histogram of all the frequencies of the letters, and then you go to the closest library, you check statistical properties of languages, and there are two candidates that get really close to this one. One is Swedish, the other one is Finnish. But still, like the most naive approach to finding the solution to this problem is just saying, OK, I overlap my histograms, and I see which one fits the data best. But it's clearly not that easy, because there are different features in the statistical distribution that, like, this one fits better, and that one fits better other features. So the way in which you solve this problem is through information theory. So we assume that languages generate strings of letters as basically sampling from a distribution. But it works. So it's like first order assumption is like the sampling is IID. So you sample from the language of writing a text, and then from this text you generate unobserved statistics. So now the question is, can you go the other way around? So you see the observed statistics and you want to guess something. So using the IID assumption, we say that the probability of observing any string x1, xn can be factorized in a product of independent factors. And then, just because we like sums, you can rewrite it in exponential form. And actually, this is particularly useful, because if now you divide and multiply by the number of elements in your string, and the number of elements is big enough, then you can apply the law of large number, and you know that this sum, this mean, will actually converge to its average value according to the right probability distribution, the underlying probability distribution. So now, what you can do is like using this approximation to just input back the relative entropy inside of this exponential. And what you see is that this quantity quantifies how well your data fits the experiment you're observing. So in our context, for example, you do like the probability distribution for each one of them, and then you compute the relative entropy between any of these distribution and the observed data, and well, you have a winner. So this sentence is actually finished. So this is a way in which you can derive the relative entropy, which is, I mean, basically finding a strategy to compare the statistics of two distributions, but it's kind of arbitrary. It's like it's just one of the many strategies you can have. So starting from this, Caesar defined a whole family of possible divergences. It's called G divergences. That basically encode the many possible ways in which you can compare different probability distributions. And this is all classical. And at least at a classical level, what is interesting is that this is a really big family. Like it has basically uncountable many possible possibilities. But locally, and locally I mean for probability distributions that really look the same, all this family collapse on a single object, and that we rewrite in this matrix form with a unique eta xy defined like this. So it's a diagonal matrix. It's positive, and it smoothly depends on the base point. And this is actually what is called the Fisher information metric for classical distribution. So an interesting result you already have for classical statistics is that for all possible contrast function, you have only one behavior at a local level that is given by what is called the Fisher information metric. So to give you a bit of an idea what this metric actually tells you, let's look at the case of Gaussian distributions. So these are probability distribution parameterized by two numbers, mu and sigma, one giving you the average and the other one the standard deviation. And basically, you can describe the space of all Gaussians by a semiplane, because sigma can only be positive. And each one of the points on this semiplane actually corresponds to a different probability distribution. So for example, going down, you get more peaked distribution because the sigma becomes smaller and smaller. Going from right to left, the point of the average just changes accordingly. So in this context, if you do all the calculation, then you get that the Fisher information takes this form. And the interesting part here is that tells you that there's this 1 over sigma square dependence in front. And this is kind of what you would expect, because if sigma is really small, then you have almost delta distribution. So as soon as you see the average value of your delta, of your Gaussian, you can infer really well which mu it corresponds to. So it's like this dependence already tells you like some properties of the distribution. Moreover, this is also a model for hyperbolic space. So we have all the geodesics there. And here geodesics means that locally what you're doing is like changing the distribution in such a way that locally you don't see that much of a statistical change, even if you're actually changing the distribution, maybe even in a radical way. For example, here, if you go like one geodesics are the vertical lines in which you just increase the noise in your distribution. Other geodesics are semicircles, and this is like corresponds to the idea that if you want to change the average value of your Gaussian, the best way is actually first increase the noise in your Gaussian, so you kind of forget, like, I mean, you lose information about your initial state, and then eventually you go back to a peak distribution again. So all of this was just statistical in nature, but there's a property that Fisher information has, and well, all statistical distances that kind of make sense should have, that is, they decrease under noise. What does it mean by this? Well, take the sentence we had before, and then you start like applying some transformation that lose progressively information about what your original language is. Then doing this, for example, here the A with umlaut disappear, you lose information about your original language because all the languages kind of collapse to the same model. So Fisher information has this property that is contractive under noisy transformation. But not only that. There's a famous theorem in this context called Chen-Stoff theorem that tells you that among all the possible metrics you can have on probability space, Fisher information is the only one that contracts under arbitrary noisy transformation. So this should be contrasted with the other way in which we derived Fisher information. That was from a purely statistical point of view. You say, I have all possible strategies that I can compare to statistical distribution with, but locally they collapse to the same object. Well, there's a purely dynamical explanation of this, characterization of the same object that tells you that the only metric that actually contracts under stochastic maps is the Fisher information, the same object. So we also have the same property for quantum maps. And everything I will say in this talk will be basically classical. But just want to tell you is like the reason why we don't do quantum here is just for clarity. Because, for example, the relative entropy we had, the contrast function we had before, now transform into these other objects in which these bold L and R are left and right multiplication operators. So like you don't have to know what these are. But the interesting part is that this unique metric we had before now becomes a whole family of different super operators that are parameterized by this F. And this is like, gives a bit of complication when you want to write things explicitly. So in this regard, I just must say that here, this family of JEF comes from the local behavior of the corresponding contrast function. There's a way to connect them. But also, this is the same family that Pett's theorem singles out. So it's the same family that contracts under arbitrary stochastic CP-TP maps. So to give you an idea of why we don't do this, this is like a table you can find in the paper. It's really useful if you want to just check whether what you have is a Fisher metric, but it's like, forget about it. I'll give you 4 examples that are particularly notable. One is the Bures metric here, that basically, whenever in physics you read about a Fisher metric, they mean this one. This other one is it's like called Kubo-Mori metric. It's really useful for thermodynamic transformations. This one is very used for defining a bias map for quantum dynamics. And this last one, I'll just give you because all the other 3, if you see, are CP maps because they are already in Krauss form. But this is not necessary. So it's like, this last one is not in Krauss form, so you know that it's not generic, the fact that Fisher information are CP. So now that you saw the complicated part, let's go to the most fun part. That is, why is this object interesting? So far, we saw that there's a statistical approach to Fisher information. And then there's the dynamical one that was a bit overlooked during the years. So I'll give you the first result of our paper, that is the following. Consider any linear map, trace non-increasing, that satisfies three properties. First, it's full rank. That means just it's invertible. Then it has to map one state in another state, at least one, and then contracts the Fisher information on the image. So just to give you, like, since this is the main theorem, I'll explain you what each one of these means. So consider the space of state. Then you have a map that acts like this. So you have basically the map. Well, invertible, you can see it from here. But it has, the second condition is that at least a part of this overlap is non-zero. So there's at least one state that is mapped into another state. And secondly, if you only focus on the part that, like, intersection of this image with the space of state, in there, where you can actually define a Fisher information, you have a contraction of the Fisher metric. If you have these three conditions, well, what turns out is that the image of phi is actually completely contained in the space of states. So this picture is wrong. The right one is like this. And this is kind of a strong result, because first we had that the Fisher information was characterized as the only metric that contracted under any physical evolution. And now we have the dual result, that is, among all the possible maps you can have, the physical ones are exactly the one that contract the Fisher metric. And here, physical is true for classical states, but since this result holds the same also for quantum state, you just need to adjoin an extra copy of the state to distinguish between a CP map and a P map. Because, of course, a positive map is the same as a completely positive map if you only look at one copy of the space of states. So we have some application of this result. First was to the study of non-Markovianity. And for the people who don't know, non-Markovianity can be described as the following. It's like you take a state rho, you couple it with an environmental state, and then you apply a unitary on top of everything. This is the definition of basically the most general, completely positive map you can have. Then you trace out the state, and you have basically this map that depends on the time s at which you stop your evolution, and kind of gives you how rho evolves in time. Now, if you want to continue the evolution to a later time, you cannot do it at this level. You have to go back, or at least not trace out the environmental state, continue the evolution, and then you have a final state phi of t. So these two are by construction CP maps. And one might wonder whether there's an intermediate map sending you from here to there in such a way that also this third, this third proper quantity is actually CP. Well, maybe surprisingly, this is the definition of Markovianity. It's like not all the maps, not all the intermediate maps are CP, and actually only the intermediate maps that correspond to a Markovian evolution are CP. So to give you like kind of an intuition of why this is the case, suppose that the intermediate map is actually physical. Then what you have is that you can actually evolve your state for some time s, and then there's another environmental state, sigma 2, and another unitary U tilde that actually implements this intermediate map. So the one going from here to here. So if this is the case, we say it's Markovian. Suppose it's not the case. Then somewhere here, there's something that breaks down. So what we know is that you can pass from this state to this state, but not from this state to this state. And if you look at the structure of what you have here, is that like the only difference is that there's an environmental state here that was traced out here. So what we have is that the evolution, in order to be physical, needs some information that was stored on the environmental state to continue progressing in time. So this is what it's usually referred to as a backflow of information. So you need, like in the first part of the evolution, you take some information about the initial condition, you give it to the environment, and then you need to take it back somehow. So now that you have some kind of evolution of what non-Macroreality is, suppose we have like the same picture as before. So this map is CP, that map is CP, and the intermediate map is actually not. So applying the main theorem of our paper, we find that contractivity actually implies Markovianity on this like adjointed space. And this is kind of surprising if you come from a non-Markovian background, because the most common quantifier there is the trace distance, defined like this. And in that context, you have that the expansion of, the contraction of trace distance is not equivalent to Markovianity if you look only at this space of states, tensor space of states. Still, there's something funny happening here. That is, if you ask now, can you operationally witness Markovianity, the situation kind of reverses. So it is well known in the literature that with the trace distance, you can prepare two states here times some ancilla. And then at a later time, you see if there's no Markovianity, an increase in the statistical distance. On the other hand, since the feature is so strongly dependent on the base point, the fact that the expansion of the feature metric can happen outside of the image doesn't tell you anything about what it's doing inside of the space of the image of phi. So actually what we find is that for the feature metric, even if it's kind of more powerful for definition of what Macroreality is, it's less powerful when it comes to witnessing no Macroreality, because you need some post-processing in order to actually witness the expansivity of your map. So Macroreality, as I was saying, tells you that the environment kind of gives you back some information about your initial state. But now, what I was discussing was the expansion of statistical distances. So it's somehow, if you're new to the subject, might look unrelated. It's like, first you have a single object quantity that is like the information about your initial state goes back like you take some information about your initial state from the environment. In this other case, you have an expansion and contraction of statistical distances that are two objects kind of property. So to connect like this conceptual gap, like to cover this conceptual gap, consider this kind of scenario. So you take two states, pi and pi plus delta, where delta is small, and the first part of your evolution is CP, so the states get closer, and then at a later time you have non-CPness such that actually these states expand. It needs not to be the case, but if this the case, we say there's an expansion of the Fisher metric on the image. And the interesting point is that the Fisher information gives you a canonical way of retrodicting your initial state through basically a generalization of what Bayes' theorem is. With this canonical way, like construction, you can retrodict both from here and from here. And in the presence of expansivity of the Fisher metric, you actually see, you can prove that the distance at a later time becomes smaller. So what we have here is that thanks to this construction, the presence of no Markovianity allows to guess your initial state better than if all the evolution would be Markovian. So this is really like a backflow of information about your initial state. So the last topic I want to cover is the definition of detailed balance. So since this is kind of more dynamical, it's like more thermodynamics property, let's look at it closely. Consider a Markov chain with only two states, I and j. And each one comes with its own population. And then you have some rates in which you jump from one state to the other. So we can define in this context a rate matrix that basically tells you how the population of each state changes in time, and basically encodes these coefficients A. And then all such matrices have a fixed point, pi, which will be like the equilibration point. So suppose now you're at equilibrium. Everything we said is generic. What detailed balance means is that this condition is satisfied. So basically, if you read it, it's like if you interpret it, this is the probability of this jump. So the probability of being in state I and then jumping to j is symmetric with respect to time. So it's the same as the probability of finding yourself in j and then jumping forward. So if you just take the definition, this mathematically takes this form. And what we can see is that you can rewrite it in this complicated form with the eta, like the Fisher information matrix from before. And forgetting about like the formula, this is just telling you that the rate matrix is self-adjoint with respect to the generator, with the Fisher information metric. So this is the classical part. And in here, you see that self-adjointness with respect to the Fisher metric is exactly equivalent to being detailed balance. For quantum detailed balance, the situation gets slightly more complicated. So this concept was defined for the first time by Alinsky, 1976. And funnily enough, this is something of a lesser known fact. He also used a scalar product. So this one is not in the Fisher family, unfortunately. But he also said, if you take a Lindbladian dynamics and you check its property with respect to a scalar product, well, it has to be self-adjoint. And this is equivalent, he proves, this structural definition that is the most canonical one. It's like if you open the Petruccione theory of open quantum system, you find this one, not the other. So now we enter the game, and we want to see whether our definition is equivalent to other three. So it's like whether saying that a Lindbladian, or let's say the dissipator of the Lindbladian, is self-adjoint with respect to the Fisher informations, it's equivalent to what Alinsky was doing in there. So this question was already posed some 10 years ago. And if you only choose one F, actually you get conditions of being detail balanced that are inequivalent between one and the other. So like different Fs gives you different conditions. And on top of that, they're all weaker than the one by Alinsky. So that means the one by Alinsky implies the other one, but not the other way around. But since we thought like Fisher information are a unique family, they should all be considered at the same time. And if you do so, you have a theorem that tells you that if the Hamiltonian doesn't have degenerate gaps, well, all the three conditions are equivalent. So now what happens if you have degenerate gaps? Well, there are three possible transitions. And to do so, we rewrite a possible state in a block matrix kind of way, in which, if you see here, pi alpha and pi beta are the population of your steady state. And you impose this condition between like alpha, beta, and gamma delta, like the defining coordinates of these two blocks. So the possible transition you can have are first among the diagonal elements. And here we just highlight ones, but actually also between all the other diagonal elements there are. And this satisfy the classical definition of detail balance, which bringing one of the population to the other side can be rewritten like this. So there's another possible transition in for quantum maps that is basically connecting the coherent terms, this one with this one, and the other one is like this other term with this other term. And the interesting part here is that also these rates satisfy the detail balance condition with the same e to the power minus omega. And up until this point, this is the same definition as Alinsky. It's like this part is already present in the more canonical definition. We actually found, though, that this is not the same we have in the presence of non-degenerate gaps. And there's another channel in which coherence can talk that is basically a kind of cross term, in which this term can speak with this term, and this term can speak with this term. And something interesting we found is that despite the fact that you have an additional channel, this is still satisfying the same kind of classical detail balance condition. So in some way, the Fisher information treats the coherences in a more symmetric way. It's like it doesn't give you a preference between these transitions and this transition. Something that instead, like the most canonical definition does. So it was a lot, so I'll just give you a brief recap of everything we saw. First, and most importantly, we have this result that being a physical map, it's in one-to-one with contracting the Fisher. So the classical result of Chentsov and Pett about the characterization of the Fisher can be actually reverted to give you a characterization that only speaks about something that was in principle a statistical distance. And this I guess could be interesting for people doing reconstruction for quantum theory, because it basically gives you a way of defining evolutions just in terms of basically information theory. Secondly, we have basically a complete characterization for the relation between Fisher information and Markovianity. Then we saw that there's a canonical construction that connects the the backflow of information given by quantum non-Markovianity to an ability of an agent to guess the initial state better and better with time. And finally, we saw that detailed balance, that is something that in principle has nothing to do, again, with statistical properties, and it was apparently just a dynamical property of the evolution, well, can be explained in terms of self-adjointness with respect to the Fisher information. So this was all I had to say. Thanks for your attention.
So you say that this theorem of the CP family Fisher contractive is useful for reconstructions. So you don't assume that you're in quantum mechanics here. This is valid for all GPTs, so to speak.
I mean, so the thing is, I tell you, if you have a linear map that is trace non-increasing, so it's like there's already a lot of structure, then physical evolutions are the ones that contract the Fisher information. So it's like, I mean, you already have to have at least the Hilbert space formalism.
Okay.
Yeah.
Yeah, and then one more thing, I didn't quite understand how non-Markovianity helps retroduction. Maybe you can explain that a bit more.
Yeah, so yeah, basically, this is something. Okay, so in classical theory, you can define bias retroduction, like literally like the bias map that tells you how to guess your initial state from the observed data, just in terms of Fisher information. It's like it's literally basically using the Fisher information to kind of well, I mean, there's a map that does that, and it's expressed only in terms of that. Quantum mechanically, it's not that uncontroversial, let's say. But there's at least one most canonical way, that is the path recovery map, that is, again, expressed in terms of Fisher information. And this connection actually helps you to map the statistical distances that you would observe in time to like how the statistical distance at the origin of time would behave. So basically, there's a canonical map that allows you to map any state close to a prior state back in time. Like it allows you to map this one back here and this one back here. And if there's a Markovianity, what you see is that your guess gets worse and worse with time. It's like basically your guess will, at some point you will just say the initial condition was the prior, because you lost any information about the initial condition. But if you have no Markovianity, then the distance between your guess and the initial condition gets smaller. If there's a contraction on the, expansion on the image.
Literally, because I don't really understand retroduction. I understand it classically.
Mm-hmm.
What to be, because you apply very good. I don't see the connection still with the Fisher metric. And what to be, I don't understand what you're doing.
Yeah, no, it's like, I mean, basically, at least quantumly is, at least classically, it's uncontroversial what we are doing. We're really doing bias theorem. Quantumly, what is funny about this result is that you don't even need a CP map doing the retroduction. We find that there are like just mathematical constructions that allows you to kind of map the scalar product at this time to the scalar product at this time, and they're kind of canonical in a sense. So like, I mean, they have some parameters in it, but once you have fixed them, it's like they contract under CP maps, and even if they are not even physical. So it's like, I mean, the quantum version is a bit weird, let's say. So like, but at least the PETS recovery, that's uncontroversial for how much uncontroversial bias theorem in quantum mechanics can be.
To ask you, this study of non-Markovianity, which community starts it? Well, why is it useful to tell if a system is Markovian or Markovian? When do you have the full description, mathematical description of a system, and you don't know if it's Markovian or not? Where does it come from?
Yeah, so basically, I'm not a Markovian guy, so I will try to kind of sell you something that is not mine. But the idea is that in the presence of no Markovianity, the error you accumulate with time at some point gets erased. And there's, for example, a really nice example that there's a really nice idea in this context that saying you want to keep some information away from any eavesdropper, and you first put it in your state, then you use a non-Markovian evolution to disperse it into an environment, and then this Markovian evolution has some backflow, but just at the right time. So it's like, for any time, you would look like your state will be fully mixed, and then at the right time, you will have a complete backflow of information. And this is called quantum safe, or non-Markovian safe. And in that context, actually witnessing that you're doing some non-Markovian evolution would be useful before actually implementing this thing and selling commercially or something like that. So there are some things for which non-Markovianity is useful, and once something is useful, you want to know whether it's happening or not.
But I was thinking, but is it really useful in the sense that is anybody selling this, for example?
This I really don't know. I don't know.
Because I can imagine a proof of security of QKD is useful because people are selling QKD systems.
Yeah.
So I want to know if it's secure.
I mean,
in this case, it seems that it's not much connected to experiments or anything practical, right? I mean, and I wonder how come, but there's so many people working on it, right? I mean,
yeah.
So I wonder what was the initial motivation, or?
I mean, I guess you would need like high level of engineering of your environment to actually have a non-Markovian evolution that is useful for something. And I don't know whether that's possible or feasible or not.
I think experiments have been made with people that really engineer
Yeah.
environments. Yes. Then I don't know if practical things have been made.
Yeah.
I mean, you could imagine that if you're building, say, a memory, this is a very simple comment. You could imagine that if you're building a memory, say, then having a non-Markovian memory can be useful in certain regimes in which you know that if you wait some time, you lose a lot, and if you wait a bit more, you get something back, right? So, I think practical things it's mostly theoretical as a field, I would say.
Who starts this field? There's physical things also in quantum information theory, right? I mean, so Hollywood in the 60s, he was already calculating channel capacities, and I don't think there was really motivated, right? I mean, who knows what he was doing? Nowadays he has a motivation, right? I mean,
Yeah.
in this case, who was the whole level of?
Yeah, well, as I was saying, it's like, for me, I will upset at least one of the co-author, but for me, non-Markovianity is not that interesting. It's like, what is interesting is that you have something that was considered as purely dynamical as a feature of your evolution, and now you can write it in terms that are completely statistical. So you take your feature information that, as I was saying, is like comes from how locally states differ from each other, and then you say, okay, evolutions that behave in this way with respect to this statistical distance are the same that other people define in another context as Markovian. So it's like this connection for me is more interesting.